Let's have a look at timber in shear. From the design perspective, the equations are just came out of the 3 So the K factors is more or less the same as what you do in the bending design. You still got to consider K24's the size factor when you're using LVL and the glue lamp, taking that into consideration, the size factor. But also by looking at it, you can see sort of gauge it. The LVL still is pretty good in terms of shear. It's slightly higher shear strength than the sawn timber and the glue lamp, because I reckon it's the mechanisms forming when trying to split. It is difficult to split through the laminations of a vertically laminated timber, rather than you have these parallel grains. It's easier to split from these, starting from these grains. I reckon that's probably the reason. So that jumps into the shear mechanism. That's what we need to understand before we jump into the calculation equations. The mechanism of the shear in the timber is slightly different than what we would visualize that in concrete design. Imagine when we draw concrete shear, so you normally have a inclined shear cracking at the support location, and a little bit like a vertical cracking at the center of the beam. They consider it as a flexure shear, and the flexure shear cracks. But in timber, it does not behave like that. But the timber design is the shear cracks are trying to split, elongate towards the timber fiber, between the timber fibers, if that makes sense. It's just it cracks from here rather than goes to diagonal, because it's hard to do. The force is really hard to go cut through each fibers, so it has to come in through a break point and then just goes through. So usually that's the crack and the failure for a timber beam. So that leads to us, when we design a shear, we are not designing the maximum shear at the support line. So we are designing a shear from 1.5 times the depth of the beam that's written in the code. So when you draw the shear force diagram, it's going to look like that. So this is the maximum shear at the support. But here is what we're going to design shear for. So let's come into 1.5 times the depth of the beam and find the intersection of the shear profile, and that is what we design as the V star. That's the maximum shear, and then we're going to check that V star against our 5 VNs to each of different members. So that's where you design our shear capacity. So make sure that your K24 is being considered, and the corrective factor K factors has been used in the design. And then your effective shear stress is 2/3 of the shear area. That is due to the assume that is a rectangular section of the shear. There's 2/3 of the area. You should know by that. You should know that at the structural mechanics. But anyway, so that's the shear design. It is slightly straightforward than the bending design. The only thing is you have this sort of the hierarchy of the strength of the member. So if you're going to use SG8, if it doesn't work, you would jump onto LVL. That's your next to the natural selection. And glue lens is normally you would pay for premium price for a premium look, and otherwise you wouldn't go for glue lens. Okay, so that's the design in shear. Thanks for watching.